In this video, we'll be practicing our interval notation and looking specifically at increasing and decreasing sections of a function. So when we have a definition for increasing, it's saying that a function is increasing whenever f of x2 is greater than f of x1. Remember, f of x is just the same thing as y, so that's just saying that y2 is greater than y1. In a graph, we're going to be reading from left to right. So if we're looking at our x-axis, there's x1 and then we have x2. It's just saying that each of those have an output associated with it. So here's y1, and then y2 might be up here. For it to be increasing, y2 has to be bigger than y1. So that would create an uphill kind of increasing section. This sometimes looks like a line with a positive slope, but it doesn't have to be linear to still be increasing. Whenever you're asked where a function is increasing, this is a key word, where, and it could also be or when a function is increasing or decreasing. You're going to state your answer as an interval of x values. So that's probably one of the key things here that people mess up, is that we're always going to be answering this with x values. It's decreasing whenever f of x2 is less than x1 or f of x1. So that's just what creates that decreasing section here as we're moving from left to right. This really kind of makes sense once we look at a graph and how we interpret this with interval notation. So we've been given a graph here of this long function here, and we're trying to describe when it's increasing. So if I look at the increasing sections, I'm going to highlight those in blue. So in this graph, we can see it goes down, hits this little point, and then it starts increasing. So that right there is an increasing section. But it increases again at this point up to that point. So those blue sections are what we're going to try to define in interval notation. Now again, we're answering where the function's increasing or when the function's increasing with our x values. So the x value associated with it is coming from this negative 2.394 or 3. So that's the first part where it starts to increase, and it's increasing all the way until we get to this x value, which is negative 1.234. So we're not going to include the y values in our interval notation, only the x values. So it's just saying from these points, so from here to here on our x-axis, the graph happens to be increasing. So we would say parentheses, negative 2.393, comma, negative 1.234. And parentheses again. Now in interval notation, we use parentheses when something is not included. We use brackets when something is included. If we look at this point right here, negative 2.393, yes, that's defined. It has a solid point here. But when we're talking about increasing, at that exact point, it's not increasing. It's also not decreasing. That exact point is where it's transitioning from decreasing to increasing. So whenever we hit that specific point, we're not including that in our interval notation. So that's why we have a parenthesis. And we're going to join this next section up with a union symbol and say, well, it starts to increase again when x is negative 0.285. And then it goes increasing until we reach positive 0.713, so 0.713. Again, we have parentheses because at those points, it's not increasing, it's not decreasing, it's turning from one to the other. And then those are the only two sections where it's increasing. So that's our interval notation for increasing. Now decreasing includes this section here. So in orange, we had this one section, and then it starts to decrease again from here to here. And then we've got one more time, then it's decreasing. Now what we don't see in this graph is that it's going to keep going on forever and ever. So we want to put the arrows here. It didn't stop it because it didn't have like a specific point that it stopped at. You would see a solid circle or either maybe even an open circle, but otherwise it's just going to keep going on forever and ever. So when we're looking at decreasing, this is decreasing this whole time. All right, we're still describing our x values. So this whole section is all of this. So at -5, our graph's gonna be way up off the screen here, off the page. So it's still gonna be decreasing though, because it's still in that decreasing section. That means -6 also would be -7. So really the decreasing sections from -infinity up until we reach that first part where it starts to turn, and it started to turn at -2.393. We do our union symbol because we have another section we're trying to join up with it, and that other section in the middle is from -1.234 until we reach the point here at -0.285. So -0.285. And then since there's a third section, we're going to have to use another union symbol and include this part here. So this happens from 0.713 all the way to infinity, because while it's very, very steep, these values to the right, when x is 5, it's still going to have an output. It's just way down negative. Same as we keep going. So when x was 6, way down negative. So all the way to infinity, it's still decreasing. Remember, these are still all the x values that we're reporting. The local max and minimum are those points where it's starting to turn. So a local maximum is when the graph changes from increasing to decreasing. Local minimums where it changes from decreasing to increasing. So here we had where it was decreasing and now it's increasing. So this right here, this point, would be a local minimum. And then we look up here, we get a local maximum. But we have another point where it's turning. So that's also a local minimum. And then this is also a local maximum. Now, if something was the lowest it ever reaches, that would be called an absolute minimum. But if we look at this graph actually keeps going down below that y value. So it's not the lowest the graph will ever reach, but it is the lowest in that one specific area, which is why it's a local minimum. So we're going to classify these extrema, and this local minimum of, this one has a y value, so the minimum is the output. So the minimum it reaches is -7.674. So that's what the graph hits. The graph hits this y value when x is -2.393. So again, x's are telling you when something happens. The y values are telling you what it hits. So the minimum again here was -0.854, and it happened when x was -0.285. If I have a local maximum, we're hitting this point here. We'll start with that one. So it's 2.512. And it happens when x, so the x value was -1.234. Local maximum, that one hits at 5.476 when x is 0.713. Do we have any absolute extrema? So in this case, there's no highest or lowest that it ever reaches, because it's going to keep going down forever and up forever. So there's no absolute extrema in this case. All right, number 4, and you can practice on your own. You can kind of pause the video and then check to see if you did it right. But we're going to be describing where it's increasing and decreasing. So this one's decreasing from here to here. So from negative 1.309, oh, sorry, we're trying to do increasing. Increasing, so that point is at 1, 2, 3, so negative 3, all the way to that negative 1.309 is increasing. So here's our increase, but then it's increasing again in that bottom section. So we're going to do a union, and I'm just going to have to put this down here. So 3.309 all the way to, not infinity, stops here at 5. Okay. Again, I'm putting parentheses for all of these because no matter if that was an open circle like this one, and this is technically closed, it's not increasing or decreasing at that point because that's the boundary. All right, and if it's a turning section like we had here, that's also not included. So decreasing here in the middle section, we see this decrease is from negative 1.309 to 3.309. And that's the only section that it's decreasing. It does say classify all extrema. So here we have a local minimum. And since that's the lowest this graph ever hits, that's also an absolute minimum. This would be our local max, but it's also the absolute max for this graph. Okay, so in this next part, let's see, increasing. We've got a middle section here that's increasing from negative 10 to 3.333, and then decreasing. And this would keep going on forever. It's not clear necessarily, but it doesn't have a point that stops it. So from negative infinity all the way to negative 10, union, and then 3.333 to positive infinity. So that looks a little rough. Okay, let's change this. All right. And then for 5, we're doing the same thing. So if you want to pause again, you can check your work here in a minute. But we've got increasing and decreasing. All right, our increasing section happens from here to here. So that would be from negative 3.606 up until 0. And then it's increasing again at positive 3.606 to infinity. Remember, it's keep going on forever and ever towards infinity there. Our decreasing section, while that is still going up, we were looking at the x values. So you don't want to put a positive infinity here. That's what the y values are doing. We're describing x values. So think about these values here. This is decreasing for all of these x values. So from negative infinity up until you reach that x value of negative 3.606. And then again from 0 to 3.306. Okay, so that's one of the biggest mistakes, is just forgetting to describe your x values. But anytime we're describing an interval notation, we're going to be looking at these x values for increasing or decreasing. So unless we're describing the range of a function, then we would use our y values, but every other time we're going to be using our x values. So if it says classify all extrema, we have these points down here that are minimums. So that's a local minimum. This is a local minimum. But since that's the lowest it ever hits over the whole graph, that's also absolute minimums as well. This one happens to just be a local maximum. So we might describe, let's say, that absolute maximum or minimum. Absolute minimum at, let's change that. The wording would be of negative 1.44 at x equals negative 3.606 and x equals 3.606. So there just happens to be 2 times that it hits that y value, and that's okay. All right, we have increasing, decreasing again. So this increasing section here is from 2 all the way to 5. And then decreasing will be from negative 5 all the way to 2. So just remember that point right there is where it's turning. We're not including it, so that's why we have these parentheses at 2. All right. 6, we're asking you to draw a graph that has the following characteristics. And so we want something that has a local minimum at negative 5. So when x is negative 5, it's going to have a local minimum. So that just means that it's going to go something like that with a U shape. Then we have a local maximum at x equals 5. So I go over to 5, put my maximum here, and it's got to go down somehow. The last characteristic is that the graph is greater than 0 when x is less than 8. So when x is at 8, that's where it's hitting 0. The graph hits 0. So that means anything before, when x is less than 8, before, we should be above the axis because that's greater than 0. After it, we're below the axis. And so there's an infinite amount of graphs that we could draw. There's one in red here, but as long as your graph has a minimum, has that little valley here at x equals negative 5, and then hits a peak at positive x equals positive 5, then we're good for that characteristic, and then it just has to hit and cross through x equals 8. Okay, so that would be one potential graph. Remember, this is not the only graph that has that characteristic. So try out number 7 and see if you can figure out how do we get this, or not just this graph, but a graph that has these characteristics. So it has to have a local maximum at x equals negative 5. So I'm going to look at negative 5, and we just know it has to have a maximum. And then it has to have a minimum when x is negative 3, or positive 3. So x is positive 3, let's go something like this. And then x is greater than 0 when x is greater than 6. So the graph is greater than 0 when x is greater than 6. So here's our 6, which means it's going to be above the graph after that section. So really that means that this won't work. It's got to be below. So let's put that point below here somewhere. Doesn't really matter. This also needs to go below, so we've got that characteristic now. And then an absolute maximum at x equals 9. So let's go to 9 and put a maximum somewhere. So that's got to have a maximum. And there is no absolute minimum. So since that's the absolute maximum, it just means that's the highest it's ever going to reach. So we can connect this here and just keep pointing down. Since there is no absolute minimum, we can make it keep going down. All right. It does say, though, that it's greater than 0 when x is greater than 6. So actually, we can't cross back over the x-axis. So I'm going to change this for mine to where maybe it has an asymptote. And it goes off in that section. All right, this one has to come down, have a minimum, so we did that. And we eventually got to hit a maximum over here. So let's hit a maximum and keep going down forever since it has no absolute minimum. So that's one potential graph. It's a little bit funky looking, but it doesn't really matter as long as it satisfies these characteristics.